So we're going to solve for the lower triangular, which is the matrix D given by 1 minus 1, 1, 0, 0. We have 2, 0, and 0, 2. Now here, I'm sure you can tell that the eigenvalues lambda 1 is equal to 1, lambda 2 equals to lambda 3 is equal to 2. So we have algebraic multiplicity to not be equal to the geometric multiplicity. So you write that the eigenvalues of the matrix D is given by this, the following, and then next you find your diagonal. I think I should write that one as diag to differentiate it from the D matrix. So the diagonal of lambda 1, lambda 2, and lambda 3 is just given by 1, 0, 0, 0, 2, 0, 0, 0, 2. So this is the diagonal of the matrix. Eigenvectors, we already know, so you have D minus lambda 1 I times V1 equals 0. So we follow the same procedure. We have 0, 2, 0, 0, 0, 2 minus, our lambda 1 is just 1, so we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Our V1 has components x, y, and z, equating to the 0 vector. So simplifying, we have 0, 0, 0, we have minus 1, we have 1, 0, we have 1, 0, 1, multiplied by x, y, and z, giving us 0, 0, 0. So we write minus x plus y equals 0. For our first equation, we have x plus z equals 0 for our second equation. We write x to be equal to minus z, therefore x over z will be equal to minus 1 over 1. So if x is equal to minus 1, it implies that z will be equal to 1. We substitute x equals minus 1 into equation 1. We have the negative of minus 1 plus y to be equal to 0. So we have y plus 1 to be equal to 0, which implies that y is equal to minus 1. So now our V1 is given by our x component, which is minus 1, y component minus 1, and a z component, which is 1. Next, we find our V2. We have D minus lambda 2 I times V2 equals to 0. So we have 1 minus 1, 0, 0, 2, 0, 0, 0, 2 minus 2, 0, 0, 0, 2, 0, 0, 0, 2, which is our lambda 2. X, y, and z equal to 0, 0, 0. So simplifying again, we have minus 1, 0, 0, minus 1, 0, 0, and we have 1, 0, 0. X, y, and z 0, 0, 0. So we see that whatever we do, we'll get x to be equal to 0. We don't need a trivial solution. We need a non-trivial solution. So what we will do is to let y to be equal to t and z to be equal to s. Doing this, we will let our v2 to be equal to our x component, which is 0, y component t, and z component, which is s. And now we can separate this to be 0 t 0 plus 0 0 s, and which is now t into bracket 0 1 0 plus our s, which is 0 0 1. So if t and s are 1, we'll have our v2 to be equal to 0 1 0, and our v3 will take the other component, which is 0 0 1. Since we have two vectors, there's no need to combine them as one. We need to separate them. So our v2 will be split into v2 and v3. So now your P matrix, which is given by v1, v2 and v3, is now given by our v1 was minus 1 minus 1 1, our v2 is 0 1 0, v3 is 0 0 1. So we have to find our P inverse, which is given by 1 over the determinant of P times the adjoint of P. Again, our adjoint of P is given by writing the elements of P. We have minus 1 minus 1 1, 0 1 0 0 0 1. So now you can follow. We have minus 1 minus 1 1, 0 1 0, and we have minus 1 0 0 minus 1 0, and minus 1 minus 1 1 0 minus 1 1. We cross out this line and this line. So our first matrix, we have this determinant, which will give us 1. The next determinant give us 0. The next determinant will give us 0. Now this determinant gives us 1. This determinant also gives us minus 1. This determinant will give us 0. Finally, this determinant will give us minus 1. This determinant will give us 0. This determinant will give us minus 1. And we find the determinant of P minus 1 into bracket 1 times 1 minus 0 times 0. And the rest are all zeros. We have plus 0 plus 0. We have minus 1 as our determinant for P. Again, our P inverse, it is given by 1 over the determinant of P is minus 1, multiplied by the values we have here. We have 1 1, and then we have 0 minus 1 0, 0 0 minus 1, minus 1 minus 1 1, 0 1 0 0 0 1. So our solution, which is given by x of t, P e of t, P inverse x naught times I plus n t plus n squared t squared divided by 2 factorial plus to infinity. We need to find our s, which is given by p d p inverse. P is given by minus 1, 1, 0, 1, 0, 0, 0, 1. Our d is given by 1, 0, 0, 0, 2, 0, 0, 0, 2. And our p inverse is also given by minus 1, 1, 0, 1, 0, 0, 0, 1. The value here multiplied by minus 1, 0, 0, minus 2, 2, 0, 2, 0, 2. So we have minus 1, 1, 0, 1, 0, 0, 0, 1. S. So our final matrix will be 1, 0, 0, minus 1, 2, 0, 1, 0, 2. So we see that S is the same as A, which implies that our N will be equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. So we have our solution x of t to be equal to our p minus 1, 1, 1, 0, 1, 0, 0, 0, 1. Our e of t, which is e raised to the power t, 0, 0, 0, e raised to the power 2t, 0, 0, 0, e raised to the power 2t. And our p inverse is also minus 1, 1, 1, 0, 1, 0, 0, 0, 1. Multiplied by I, multiplied by x naught. You can simplify this and then get a matrix multiplied by x naught. That will be your solution. Now, in each of the cases, we were told to find the subspace of the matrix. The subspace for this matrix is an unstable subspace because all the eigenvalues that we had were positive. So we have the span of all the vectors. So we have v1, v2, and v3. Now, a word of advice. I skipped some processes when I was finding for eigenvector, which is v3. The actual process is to only let y to be equal to t and let z to be equal to 0. Then you will find this eigenvector, which is related to v2. And when you do it again, you will get x to be equal to 0 again. And then you let z to be equal to 1 this time, and let y to be equal to 0, so that you get 0, 0, 1. First step is to let y equals 1 and z equals 0. You assign them values so that you get your v2 to be equal to 0, 1, 0. And then you square your other values, which is you find d minus lambda 2i all squared multiplied by v3, which is equal to the 0 vector. And after doing this, you will see that you will get x to be equal to 0, and we will not have any value for y and z. This time you will let y to be equal to 0 and z to be equal to 1, which will give you this vector here. So that's the right process. As I've listed here, you can follow them and arrive at the same solution. So our span stable subspace E of S is given by the span of the vector v2 and v3, whilst the unstable subspace is given by the span of the vector v1. Okay, so this is given by the span. v2 is given by, we have 1 minus 1, 0, and the other one will be 0, 0, 1. And for this, we have the span to be equal to 1, 0, 0. The eigenvalue corresponding to this eigenvector is positive, and the eigenvalues corresponding